So from this point, I can see you guys. It's recall my memory 2 years ago because that's the first classroom I start teaching at Phillips College, and that was an early morning class, digital electronics, engineering 338, 2 years ago, starting at 8 a.m. And I still remember there was a girl sitting there, and she was from a psychology major, and she emailed me before the class and saying if I can give her override since she doesn't have circuit one, doesn't have all these things since she's in psychology major, but she just want to learn digital. I just wondering why, and then she sent me an email, have all these projects he worked at home. So she has a breadboard, she has a Arduino, she has all these things. So I'm pretty sure she can handle digital. So I gave her override, and she was in my class. I think the incentive is since her boyfriend was in Silicon Valley, and he was in a physics major in our department. He took digital, I think, with Dr. Hicks by that time, a few years ago. And he was super interested in that and started learning IPGA by himself. So he can program with the hardware description language on the IPGAs. Can see all this digital stuff working on the board. And he got a job after he graduated from the physics major, and he got a job in the Silicon Valley working with IPGAs to design the control system for drones in the Silicon Valley. Pretty interesting. And she just want to follow him and just want to move to Silicon Valley as well after she graduated because she need a job, right? That's really a practical problem. So before she graduated, she took digital and play around with IPGAs, get more experience, and also got a job at Silicon Valley. Is that interesting? Yeah. Get self-motivated since she knows it's important stuff to learn. So in summer we have fundamental logic offered, right? You know that. That's where the story come from. All right, just let you know, important. All right, I'm thinking, so from the first day, actually second day, before we move further with all this time delay and phase shift and all these things, I'm pretty sure you already forgot all these circuit 1, circuit 2 stuff. So I probably want to answer some questions you have for a while. So for example, what is E? Okay, sometimes they use E as voltage, right? Yeah, E. I mean for the natural constant. Yeah, so what is that? Natural. Why is natural? I just couldn't see what word is natural. It's the letter. And why is a constant? Something, right? I don't even know. And I didn't know actually. When I was in college, the professor just said natural constant, natural constant. I just never know why it's natural and what does that mean, right? And it's being used in electrical engineering a lot to represent signals. And why do we use E to represent signals? Actually, E are being used in a lot of places. In engineering, in physics, in math. It's not just came from one place. It's kind of magic. I think the starting point is a compound interest discovered by somebody like a few hundred years ago. But not limited to that. I mean, just want to tell you like where that comes from, right? Compound. Thinking you may know what that means, right? If you have $100 in the bank, and for example, the annual interest is 100%, so that's your total amount of money after 1 year, right? Okay. So what if they divide that one into, for example, 6 months. There's a 6 months interest, which is 50%. So what's the final amount of money after 1 year? So 50% as 6 months interest rate. So in 1 year, you got 2 6 months, right? So it's going to be 1 plus 50% and times this. Compound interest, because you get some more money in the first 6 months. So that interest will be added to your original money and then being used as another principal and times the interest rate afterwards, right? So that will be a little, so which one is more? Of course, the second one, since you got interest, which is more money than you originally have, right? So this is a little bit more. I mean, what about I divide this 1 year into 4 seasons, and I'm using 25% as the interest rate. So it's going to be 100 times right? Which is more? The third one is more. And 25% is also 1/4, right? So we can write it down the same way. No difference. You divide the 1 year into 4 parts, and you have 24. You have 1/4 as the interest rate, which is also same, right? So what if I have n? I divide 1 year by n parts. So it's going to be 100 times and you are thinking this one is more than that. This one is more than that. This is more than that, right? So if I do n, which is infinity, can I get $1 billion for $100? So this is getting more and more and more, right? What you think? So pay attention to here, this part. For example, n is huge. So what is this? 1? Let's think about that. So when n is larger, this number is smaller. This is larger. So the base is smaller, but the exponential number is larger. Are you getting a larger and larger number, or is it getting smaller, or is it getting larger? It's competing, right? So what's the final result will be? That's E. So you won't get a billion. What's the maximum amount of money you can get after 1 year? 2.7 times 100. You cannot even get $300 out of it. Just $271. Not even $272. You just can't. Is that interesting? That's where it can come from. So what's the relation from this E to the E we are going to use for the signals? No relation. I mean, just I told you in the beginning of the class. So E are being used in many places, in physics, in math, in signals. This is just like one of that, right? Just let you know where it come from. This is magic natural constant. You don't believe that? Let's try one number. You want to try one number? Let's try 1,000. So 1,000, 1 plus 1 over 1,000 will be 1.001, right? Exponential 1000 times, boom. Right? It's not even 2.72. You'll never reach 2.72. It's gonna be super close to 2.71, blah, 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 something, right? So what's the curve look like, you think? Just think. Here's n, here's plot it. Still not. Look at, start from the beginning. What is this? 2. What is this? 4. It's 2.71. How did I get 4? Okay, so what is this? So 1.5 times 1.5, right? What is that? 2.25. Closer. What is this? I don't know. I mean 2 point something, right? 2.3 probably something. Okay, so it increases faster in the beginning, but getting slower and finally closer and closer to E, right? So it's faster at the very beginning, which means it's gonna be something like that, right? That's E. So another question you may have. What is J? Yep. Or sometimes you probably see I in there. And what is that? Imaginary number, right? Why do you want to use it? J is James? Oh, J is better? Yeah, I like J. I'm going to use J. So, what is this? What is this? Capacitor, inductor. So what's the impedance of the capacitor? So capacitor will block DC voltage, but pass AC voltage, right? How can capacitor pass the AC signal? So what's a capacitor? It's 2 metal plates with a dielectric material inside in the middle and 2 metal wires connected to the 2 plates. It's insulator in the middle, right? How can I pass electrical signal from there, from here to here? It's charging and discharging. So when it's charging to here, you probably get positive charges, and which will attract negative charges to this plate. And charging, discharging, so the charges are coming back and forth. So it seems like the AC signal is passing, but actually it's not. Right? There's no contact. It's just attracting, charging and discharging like that. So since it's considered as passing the AC signal, so there will be an impedance, which has a parameter of when you are passing a AC voltage across the capacitor, you'll see an impedance, which is pretty similar to the resistance of a resistor when you are passing a DC signal to it. So what's the impedance of the capacitor? Yep, there's a frequency involved, but what's the impedance? You all forgot it. So you came from circuit 2.
Yeah, no, it's 1 over the S.
Oh, close. Yeah. So it's 1 over J omega C. What is J? No, J is this. J is square root of -1. I know you don't know why, and it's confusing, but I'm going to explain this to you pretty soon. So today is asking some questions you have, right? So we'll answer some questions you have. We'll clarify all these things. So J is this, omega is, it's called angular velocity. So what is that? 2 pi f. Omega is 2 pi f. What is f? Frequency. 1 over t. What is t? Period. What is 2 pi? I don't know why we use 2 pi. 2 pi is something in the circle. And that's a capacitor. Why? Period. Yep. It's called unit circle. All right. How many? What's the entire angle of this circle? 2 pi. Zero. Pi over 2. No. Pi over 4. Pi over 2. I just divide this circle by all these sections. And I plot the amplitude of these points. What's the amplitude? You project this length to the y-axis. That's the amplitude. Right? If the radius of the circle is 1, what's the amplitude will be? R is 1. So here is 1. Here is theta. What is this? One theta. What is this? Wait. Am I doing something wrong? Hey, that's a triangle, right? And I know so here is vertical, right? Theta 1. What's this? Is that 1 times sin theta? Which is sin theta. Okay. So now let's project this one to a sine wave. Since we know the amplitude are points of sin theta, when you are changing the theta, it's going to be a sin theta. Right? Agree with that? Now let's see. This point, I project this point to 0 since the amplitude is, or this point is. Does this guy has amplitude? No, it's 0. Right? So 0. What about this? This point? It's pi over 4. Right? And here's amplitude. And then this point, pi over 2. And this point, is that this? For cert, pi. Here. And then this point, pi, no amplitude, so 0. And this point, here. And this point, what's the x-axis? 6 over 4 pi. What's this one? 7 over 4 pi. And what's this? 2 pi. or 8 over 4 pi. And amplitude is 0. You plot this curve, you will see that it's a sine wave. And this is called unit circle, and that's a sine wave. So you can project all these points to a sine wave. And we are trying to use this since the circle is kind of cycling, coming back to the original point, and the sine wave is doing the same thing. So it's oscillating to the largest amplitude and then come back to 0, and then go to the most negative amplitude and then come back to 0, and then it's going to just repeat, same as a circle. Okay, why do we want to use a circle? Why do we want to use 2 pi? It's another question. Now let's see. Remember omega? 2 pi f, angular speed. It's not a movement speed, right? It's not in terms of the distance, but it's in terms of angle, right? For example, this is a circle. What's the perimeter? 2 pi r, right? What is r? Radius. So how many r's do you have in one circle in terms of length? No, for a circle. So I can use a string to form a circle, right? And the parameter, how to pronounce it? Parameter. Huh? Parameter, okay. The perimeter of the circle is 2 pi r. And I make it straight. So how many r's do I have in this string? 2 pi r's. Right? I got 2 pi r's. So for example, this is r. So this is about r, right? So this is r. And this angle here is 1 radian. How many radians do you have in the circle? 2 pi's. All right? So you have 2 pi radians divided by what? Divided by the period. So we get the angular velocity. Is that making sense? For angular velocity, since we have 2 pi radians, 2 pi rads, right? This is 1 rad. How many rads we have? 2 pi. So we have 2 pi rads. 2 pi rads divided by the time will be the angular velocity, which is, that's a unit, radian per second. That's the unit for omega. Okay, making sense? There might be something else I want to tell you after this. All right, so why sine wave? Why cosine wave? Why not something else? Why not square wave? Is that boring? It's okay. I couldn't remember the equation, this quadrature function, pretty long. All right, so being used in the communication system, like wireless communication, RF, we need a sine wave to be used as the carrier. So which means because you know, if you have a low frequency signal, you cannot transmit that signal through the RF, through the antenna. You know what I mean? So when the frequency is low, you don't have enough energy to send it out to the air. So you have to use a carrier, which is usually a sine wave. So you can increase the sine wave to a very high frequency. So that frequency, that high frequency signal can carry your low frequency signal and to be sent by the antenna. So you can do the communication, like mobile phone, you can call China, like talk to them. Because they have a carrier, which is the high frequency signal can be transmitted using antenna. So that's why we sometimes use different frequency bands, like 2 gigahertz, 1 gigahertz, 3 gigahertz, and we need to modulate the frequency and amplitude of the carrier signal, which is the sound wave. So there's a way to do that. It's called quadrature signals. Which is another magic stuff. So the definition of that one is the summation of the in-phase sound wave and the quadrature sound wave, which is pi over 4, 90-degree phase shift. You don't need to worry about that. Just let you know what's going to happen. It's magic. But you don't need to know very deep in there for analog or digital communication. That's totally another course or major. So the quadrature signal, sound wave, so the summation of the in-phase sound wave and so the in-phase sound wave and the quadrature sound wave, the summation of these two sound waves is still a sound wave. But the thing is, you just simply change the amplitude of the quadrature sound wave, the summation, which is also a sound wave, the phase and amplitude of that result, or that summation, or the result signal, which is also a sound wave, can be modified easily just by changing the quadrature sound wave's amplitude easily. Can we verify that? You know what I mean? So you have two sound waves, which has a 90-degree phase shift, right? When you want to generate any arbitrary signal to be used as a carrier for the RF communication, you just need to simply, so you are doing addition operation in the circuits using a summation amplifier or something, right? Adding them together. You just need to change the amplitude of the quadrature sound wave. So the summation of these two signals, the phase and amplitude can be changed by whatever you want to modify that signal. So you can create different types of signals with a different phase, different amplitude. Okay, it's being used in communication system for I don't know how many years. Probably it's been 60, 70, 80 years, still being used for now. But we can verify this really quick. How can we verify that? Good question. A good professor will answer a question with asking a question. That's what you really do. LT spice. Don't be that serious, so simple. How can I do that? I just generate the two sound waves and just add them together, see if I can get another sound wave with a different phase, different amplitude. It's magic, right? You got two sound waves, you don't know what's going on inside, but finally you get a result. And it's a sound wave, it's nothing else. Probably wanted me to code it up, I won't. But just use. You are the person who will code it up. Right click, advanced, sound wave, DC offset, 0, amplitude, 1, frequency, 1K, delay. So this one I don't need any delay. But for the second one, it's a quadrature signal, so which means it's a 90-degree phase shift. And I will just show you how to do it. You don't need to know that for now. You'll understand this later. So right click, sine wave, DC offset 0, just keep the same, keep it consistent. Amplitude, I just do 1 for now. I can change it later. Frequency 1K, just same signal. But I'm going to generate the delay. 90-degree delay means a quarter of the period. No, oh yeah, a quarter of the period, right? A quarter of the period. What's the period right now? 1K hertz means 1 millisecond. So a quarter of the period will be 250 microsecond. 250 U. Let's plot it. I cannot because I don't have a command right now. So do a transient analysis, time domain analysis. And if I want to show probably 2 periods or 3 periods in the monitor, I want to start from time 0 and stop at 1 second. No. What's the period? 1 millisecond. So 1 second, I'm going to have 1,000 sound waves. And they will be squeezed together. You won't be able to see a sound wave. It's going to be a square block, right? Solid color. You want to see what that looks like for those guys? Never seen that before? Let's do it. Boom. Hey, no, I haven't. Just 1 second, okay? That's a sound wave. I can see that. Also a sound wave. All right, different color. All right, let's change it. I want to see 3 periods, okay? It's 1 millisecond per period. So how long? 3 milli. All right, 3M. Okay, what's next? Add another plot pin, drag this up. I'm gonna do the magic addition, summation. Right now, let's do it. Add traces. I don't have V1 plus V2. Just manually do it. Click this, plus this. Boom. Ooh. Still a sound wave with a phase shift. See? It's not in the same phase as either of these 2 original ones. Now, the transmitter need a different sound wave. For example, I need a different. So look at the amplitude right now. What's the amplitude? Let's move it to the same plotting and see what that looks like. All right. You add 2 sound waves, which are so the 2 sound waves has a 90-degree phase shift. Then the result is still a sound wave with a different phase and amplitude. And if you want to change the phase and amplitude of this signal, it's like a function generator, right? You just want to change that. You can just simply change the amplitude of the quadrature signal, which is the blue one. Let's do it. Right click this guy, change the amplitude to 3. Remember, what's the result right now? What's the result? What's the B1 plus B2? It's like 1.5, and so the peak is in the middle of these 2 signals, right? Pay attention to that. Right. So I changed the signal amplitude to 3, and let's do it again. And don't forget to click simulation after you change the parameter here. It's different, right? So there's an equation, there's a math equation to, to show you how this happens mathematically in numbers, in theory. We just, just for fun, just trying to demonstrate 2 sound waves as the 2 sound waves, 2 quadrature signals together, you are getting a sound wave, and you can change the amplitude of one of the 2 signals, so you can get different phases and different amplitude of the output. That's what people are using in the real life for wireless communication. Okay? And the equation dominates this behavior is this. So AI cosine 2 pi f0t plus AQ. So I means in phase, Q means quadrature. So AI is amplitude of this cosine signal. So you know the cosine signal and sine signal has a 90-degree phase shift, right? They're the same signal, but they just have a 90-degree phase shift. So these two signals are quadrature signals. So AI, AQ.
That's what that is. Oh, AQ sign.
Yeah, AQ is amplitude, is the number constant. AQ sine 2 pi f 0t, and the result. So see, that's what we did in LT-SPICE. So the result of this summation is this. That's what you just saw in LT-SPICE. Tangent, the inverse function of tangent AQ over AI. That's a calculation. You just saw the simulation. See these two signals, cosine and sine. Remember that? Do you know that? Cosine and sine. So that's cosine, right? And that's sine. They are exactly the same signal, but with a 90-degree phase shift, right? So that's why these two signals are, if this is in phase, then this guy will be the quadrature signal, okay? And I'm changing the amplitude here, AI, AQ, the relative amplitude, you can change it, whatever you want to change. I just change A and AQ by changing the amplitude of these two signals, and these two numbers will be carried in here as well. So it's not only changing the amplitude of the summation. See, here's the amplitude, right, for this cosine. When you are changing A and AQ, you're changing the amplitude of the result. Also, you are changing the phase as well. See that? That's why you see the phase and amplitude change are happening at the same time in the simulation. Because here and here, by just changing the amplitude, right? So that's the phase shift. That's the change of the amplitude. Okay, so you know where this kind of thing came from. And let's hold on here, and we will get into J, and then we'll come back and you'll know why we use the quadrature signal and why J makes sense. So J. For e to the case power, this number, we expand this into its Taylor series. Oh my God, nightmare. Taylor. Oh, Taylor series. 1 plus k plus 2's factorial, k to the second power. One more, right? It won't stop. So that's a Taylor series of e to the case power cosine k. 1 minus this plus this minus this, just all the even numbers, plus this sine k. K minus this, all the odd numbers. So it looks like I can probably do some modification to something and put them together. I can get EK. So it looks like EK is a function of cosine k and sine k. Can you see that? It seems like as the same terms, but just changing the signs, right? Now let's see another thing. I replace k with square root of minus 1 times k. Just plug in this part into here. Just replace all the k's with this guy, with this times k. And now let's see what that looks like. 1 is not being changed since there's no k in there. And k definitely changed. Right? What's next? Plus what? Or minus what? Next. This one. Plus or minus, think about that. Because k, the third power, is going to be minus, right? Oh, it's minus or plus? Minus. This one? Plus or minus? Plus. This. Still plus. Right? Next. Minus. Next. Still minus. Next. Plus. It's an even number, so plus. Oh, I missed this. The last one. Still plus. All right, so that's this one. And now let's take a look at this. This guy, this guy, this guy, this guy, this guy. What are they? Look at these terms. They're just cosine k. You see that? What are these ones? Sine k. Nope. If you take square root of minus 1 out, it's going to be sine k, right? It's just, so these terms are just this. So what's the result? Well, this one equals to Euler's formula. And now this number makes sense. Otherwise, it doesn't make sense. Only makes sense here. That's an imaginary number. And why we need that? Signal in phase, signal in quadrature. What? They are being separated by the J. But do we care? Now let's see what this one looks like. Next page. So there's a name for this guy, for this thing. There might be another form, but the thing is, this a real part plus imaginary part in this way, in electrical engineering, in the signal domain, it's called phasor. So still remember this in circuit 2, circuit 1. So what is a phasor? That's an imaginary plane. That's a real plane. It's unit circle. I drew a bar here. And I can use a phasor to represent the bar, to represent the amplitude and the phase of the bar. Can I? So what's the phasor? You think? I mean, by whatever you learned, just trying to recall your memory. What is a phasor? Amplitude and phase, but make it more intuitive. Make it like anybody never get educated, you can still understand that. No, it's hard. Sorry. So the phasor is a bar which has both amplitude and phase information in there. So the phasor is the bar here, right? And why this one can be used to represent the bar? You see here, what's this? It's a unit circle, for example. And what is this? What is this? If the angle is K, right? So that's cosine K, that's sine K. Okay. So what's the amplitude and what's the amplitude is the length of the bar? The angle is the bar from the bar to the original so the x-axis. So that's the face of the bar, or the face of the phasor, or the face of the signal. So we can simply use a bar like that, which is a phasor, to represent the sine wave. So what's the amplitude of the sine wave? Let me know. The maximum amplitude. I know it's changing, right? It's oscillating. But what's the maximum amplitude of this bar? And it's a unit circle. 1. Because when this oscillate to here, what's the length? Remember the sine wave? What's this? 1. Because this is a unit circle, which means r equals to 1. So that's r. And y is 1? I mean, you can see here that it's sine k square plus cosine k square and square root, right? So this is 1. And what's the phase? Which means what's the angle? What is k? It looks weird, but it is what it is, right? So what is k in tangent k? What is K in tangent K? It's an inverse signal of tangent K equals to K, right? Inverse function of tangent K. So that's tangent K. That's inverse of tangent K. That's K. So you get phase, you get amplitude. So this bar, which is the phasor, carries both the information of phase and amplitude. And we're using the phasor to represent signals in electrical engineering. So here's one reason we want to use it. I'll show you. Still have 5 minutes, right? Still got 5 minutes. So instead of using this, we prefer using AI cosine. We prefer using the phasor, and I will tell you why. J, got a J, you got a, it's a phasor right now. So this one equals to this. So got E involved because it's you got imaginary number omega t plus the phase shift. So instead of using this, the quadrature, the addition of the two quadrature signals, remember that we see in the simulation, we can add the two sine waves together so we can get another signal. Instead of doing that in the circuit, we prefer doing this. The reason is this one is easier to be used for division and multiplication. It's just a simple addition. Why is that? EA times EB is what? How to do a signal multiplication over here? Takes time. Hard to be implemented in circuits. What is this? Yeah, just a simple summation and subtraction. I can easily do it using a really traditional operational amplifiers. All right, there's several other things I want to cover here. Remember in the beginning of the class, I mentioned so that's their impedance. Why is that? It's a capacitor. So why the capacitor has an imaginary number in there? Yeah, let's think about that. So here's a AC signal, here's a capacitor, and the voltage is, here it is. And the voltage is charging the capacitor. So what's the current? C dV dt. Do you remember that? If you forgot, just go back to your notes or something. So this is a definition. So when you are using a voltage source to charge a capacitor up, so that's the current flow into the capacitor. And now let's see. C d dt. What is that? T? No, do you have T? Oh, you have T? Right? Then what's the resistance? You get a current, you get a voltage. What's the resistance? It's not R, it's actually called Z, impedance. So that's a conclusion. Very simple conclusion. And we're going to use this for throughout the semester. But I just want to know, I want you guys to know why there's a J in the impedance, which is weird, right? What about this guy? So we're going to use a current source to charge a inductor, and the current is a sine wave. It's AC signal. Why is this a sine wave? Why is this a sine wave? This equals to what? Remember that from the Taylor series? So this is a sine wave. Why? Because this is a phasor, right? So this is a sine wave. This is a sine wave. AC signal, sine wave, and current charging up the inductor, and you are getting a voltage across the inductor, which is LD IDT, which is LD, which is what is Z? V over I. What is V? This is V. Wait, J omega T, right? Over what? What's the impedance of the inductor? Okay. All right. We cannot cover everything I expect to cover, but I think it's fine. Wednesday, so Friday we'll cover more, so we are able to work on the homework. I probably will delay the due date for the first homework. Okay. So refresh your browser. You'll see that.